Hi, I'm Travis Connor, and this is my Lab 6 Magnetic Molasses. For our introduction, the goals of this lab were to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet falling through the aluminum foil tube computationally, and compare the computational model with the observed data. Overall, the findings I had were the average time for the magnet to fall through the tube was 1.42 seconds. For a magnetic dipole of 1.85 ammeters squared, the predicted time was 0.85 seconds. For a magnetic dipole of 3.9, the predicted time matches the observed time. Faraday's law relates the integral of the dot product between an induced electric field and the length of the outer edge of a closed area to the negative derivative of the magnetic flux, where the magnetic flux is equal to the dot product between the magnetic field and the area where the magnetic field flows through. In this lab, the first equation used for the charge in the magnetic flux is this right here. Magnetic field E produced by the change in magnetic flux follows a loop and is in the same direction as the current. Magnetic force on a wire loop is equivalent to the cross product of the current multiplied by the L vector of the magnetic field, where the L vector has a magnitude equal to the length of the wire. When considering the magnetic force on a loop, the following equation is derived. Also, Newton's third law is used. The magnitude of the magnetic force on the loop is equal to the magnitude of the force on the magnet by the loop in its opposite direction. Also, Ohm's law is used. The current is related to the quotient of the potential difference and the resistance. The potential difference in this lab is the EMF induced, which is equal to the negative charge in the magnetic flux. So for this, we have the following visual model where the system was a falling magnet and the surroundings was aluminum flow in the earth, producing two forces, force one being force due to gravity and force two being the force due to the magnetic field. So for the procedures for this lab was to mark the north pole of the magnet, measure the mass of the magnet, measure the falling characteristics of the aluminum tube, drop the magnet through the aluminum tube 5 times, determine the time for the magnet entering the aluminum tube to the time the magnet leaves the aluminum tube. Then using Python, computationally model the magnet tube interaction, and then compare the observed results with computational results. So for the observational results, you can see to the right, the average time was 1.42 seconds. The length of the tube was 0.27 meters. The width of the tube was 0.02 meters. The inner radius was 0.15 meters. Total radius of those two added up. The mass of the magnet was 0.023 kilograms. So here you can see the computational model, initial conditions, and constants. Next, you can see the computational model, magnetic field and magnetic flux. And now you can see the computational model, simulation loop. Here, the computational results can be compared between the two different magnetic dipoles, with the 1.85 magnetic dipole being on the right side and the 3.9 magnetic dipole being on the left side. So for the discussion, the magnetic dipole moment found in the previous lab was used. The simulation predicted that the magnet would take 0.385 seconds to pass through the tube. This did not match the observed value. The magnetic dipole was increased to 3.9 am squared. The simulation predicted that the magnet would take 1.437 seconds, which is very close to actual value. The results suggested that the magnetic dipole from the previous lab may be inaccurate and that the 3.9 am squared may be a more accurate value for a magnetic dipole moment. So from possible sources of error, contact and or friction between the magnet and the tube. The magnet will make contact to the tube while it's traveling through, and this will cause friction force within the tube. Also, air resistance within the tube. Timing error, taking the video and actually sorting out when it started and when it came out the tube. And also measurement error. We use a meter stick to measure the tube, and this could be off because it's not as accurate. And to answer the question, first what if question, the magnet would fall with a slower speed because the force on the magnet from the loop would be much closer in magnitude to the gravitational force. And for the second question, the magnet would fall with greater speed because of the magnitude of the force on it would be much less than the force of gravity.